Alright, here's a video covering how we deal with projectiles that are launched at angles. So I'm going to talk about what does this mean about my initial velocity when I shoot it at an angle instead of horizontal. And then I'm going to do two examples, one to start out simpler, and then the last one will be just like our angled projectile motion lab. I'll just use different numbers, but you'll use the same process when solving that one. So here we go. So first, if I draw an arrow representing the velocity of this marble coming out of the launcher, it's going to launch diagonally in that direction. So what that means is some of this arrow, velocity vector, is pointing in the x direction. So that's going to be my initial x if this is my total initial velocity. Let me get a different color here. This arrow is also pointing up. That is going to be my initial y velocity. So in this initial velocity represented by the blue vector, it's both pointing to the right and up. So how do I figure out what these components of this initial velocity are? Because I can only put this x and this y in my chart, because I have to have one for each side. So let's talk about that for a second. So we're shooting our marble with an initial velocity at an angle. Some of that velocity is pointed to the right. Some of that velocity is pointed up as well. So a piece of information I have to know here, and you're going to get this in your lab, is what angle am I shooting this at? Because of course I can shoot something diagonally, but the angle there matters, because if I increase this angle, then this y component is just going to get longer. If I decrease the angle, this x component is going to get longer. So it's important to know exactly what that angle is, because it changes my components of my velocity. So let's start with the x component. Well, obviously I've made a right triangle and I have an angle, so I'm probably going to use SOHCAHTOA, keeping in mind what the sides of my triangle are. This x component would be adjacent to my angle because it's right next to it. This y component would be opposite the angle. And then, of course, this would be the hypotenuse. So if I write out an equation that involves the x component, and say I already know what speed this is being launched at, so I know what the length or the value of that blue arrow is, that's my hypotenuse. I'm looking for the adjacent, so let's start with cosine. So the cosine of that angle is going to be the adjacent, which is the x, over the hypotenuse. So if I solve this for the x component, I get initial velocity times the cosine of the angle. We can go ahead and box this in, circle it, star it, put it in our notes. This is always how I get the initial x velocity. So we're doing this once, but now and forevermore, this is my initial x velocity equation. So let's come up with one for the y direction. So my initial y velocity is opposite, so let's use the SO part of SOHCAHTOA, which is sine. So the sine of that angle is the opposite side over the hypotenuse. And again, the same way, let's solve for the initial y velocity. Well, it's just initial times the sine of that angle. Just like with the horizontal, the x component, this is always how I'm going to find my initial y component of my velocity to put in my chart. So let's do two examples. So here's our first example. Let's say I shoot something from ground level at 100 meters per second and at a 30-degree angle. I know it's going to follow this path as it travels through the air, and let's say it lands on the ground some distance later. The goal here is, what is that range? What is that horizontal displacement? So if I'm looking at my chart, which I'll make real quick. Alright, here we have our chart. I know the x acceleration is 0 meters per second squared. The y is negative 9.8 meters per second squared. And what else do I know in this problem? Well, I know it's starting at ground level and ending at ground level. So in terms of my y position, from beginning to end, it did not end up above or below where it started, so this delta y should be 0. In terms of vertically, its initial and final positions are the same. So we'll say delta y is 0. Delta x is what I'm looking for, so I'll put a question mark there. So now, we just went over, how do I figure out what this x and y initial velocity are? Well, I'll use the same coloring scheme. This initial x velocity is initial velocity times the cosine of my angle, which is 100 cosine 30, which gives me 86.6 meters per second. Sorry, that's pretty nasty. 86.6 meters per second. Then my y component is going to be initial sine theta, which is 100 sine 30, which ends up being 50 meters per second. And notice they are both positive because this is pointing to the right and it's pointing up. Both of those are positive directions. So if I look at my two sides here, just like in general, what we've seen before is the right side is, or the y side is the one I can actually solve for time with because I have 3 variables. Again, we're usually going to use our second equation. So now, how is this going to be different than what we've been doing before? Well, let's put in numbers. My delta y is 0. My initial y velocity is not 0 like it used to be with the horizontal. It's 50. So that t there does not go away anymore. I've got 1/2. Acceleration is negative 9.8. T squared. This next line I will take and multiply out the 1/2 and negative 9.8. And so I get 0 equals 50t minus 4.9 t squared. This is a special case because I see I have a t and a t squared. I can't just combine those. I can't subtract those terms because they're not the same. But luckily, the left side of my equation is equal to 0. So let's try to just add 4.9 t squared to both sides and then see what I can do from there. So I get 4.9 t squared equals 50t. I can divide both sides by 4.9. I would get t squared equals 10.2 t. And now, if I know that t squared is just t multiplied times t, I can then recognize that I can divide both these sides by time. It divides out the time on the right side, and it gets rid of one of these in the squared term. So I'm left with time equals 10.2 seconds. So that's what I'm going to put here. I'm going to put 10.2. It's the same for the x. That doesn't change because it's angled. The time is always the same. So 10.2 seconds. Now let's move to the x direction. There's only the same equation from last week or 2 weeks ago still applies to the x direction. It's only displacement is velocity multiplied times time. So my displacement here is going to be 86.6 multiplied times 10.2, which if I do that in my calculator real quick, we get 883 meters. So that would be my horizontal displacement. So the only thing different about this problem as compared to before is now I have this extra step in the beginning of figuring out what these initial velocities are. My initial y velocity is no longer 0, and so that changes kind of, for this problem, what the steps in my equation how to solve are. But still, this really wasn't that bad to solve, and we solve this type of problem the same way every single time. You may see one just like this on the test. So what if I alter this to look just like the lab? So in the lab, same deal. We're shooting something at an angle, but we're allowing it to land below where it was launched. So there is a displacement in the y direction now. So I kept the same numbers from last time. Let's use 100 meters per second and 30 degrees. Why do I want to do that? Because if I go ahead and fill in my accelerations, it keeps me from having to do that sine and cosine over again. So I already know my initial velocity in the x is 86.6. In the y, it's 50. We just did that in the last problem. Now I know my delta y is no longer 0 because it ends up lower than where it started. How much lower? Well, because it ends up lower, I'm going to make it negative, and it ends up 100 meters below where it started. So let's say this is something like maybe a cannonball launched from a cannon off a cliff. Ends up 100 meters lower from where it started. So again, I have 3 variables in the y direction, and again, let's say we're looking for how far will it travel in the x direction before it hits the ground, which is what the lab is solving for. So this angle projectile lab is one step. This is how I do that step. So let's write out our second equation. I forgot the t there. And let's substitute our variables. So this entire right side of the equation is the same. I've got 50t minus 4.9t squared. How did I get that? Well, 1/2 times a is 1/2 times negative 9.8, which is negative 4.9. The difference now is the left side is not 0. The left side is negative 100. So that little trick I pulled last time where I added the 4.9t squared to the left side, that can't work anymore. Because if I do that, I get 4.9t squared minus 100 equals 50t. And I did that last time because I knew I was going to be able to divide by t and cancel one of them out. But I can't do that now because I've got this minus 100 sitting there. So where do we go from here? Well, you may recognize this as a quadratic equation, or you could recognize it if I wrote it like this. Let's move the 100 to the right side, so let's add 100 to both sides. I'm going to write the 4.9t squared first. Then I'll write the 50t. Then we added 100 to the right side. Well, this looks like the standard form of a quadratic equation. If I set it equal to 0, you may have done something in math where you've factored this into two expressions that were multiplied. But in reality, and especially in the lab, most of these numbers are going to be decimals. And decimals are not easy and almost practically impossible to just factor using methods we've learned in math. So how am I going to figure out something like this? How do I solve for time? Because I need time to put in my chart to get my displacement in the x. Well, at this point, in my notes, I would probably just write, let's use an online quadratic calculator. Because I want to use the quadratic formula, which if we remember, was opposite of b plus or minus square root b squared minus 4ac over 2a. Solve that out, I would get time. This is all well and good. Let's use an online calculator that will do this for us. As long as we can get it set up where you recognize what the a, b, and c are, I don't care that you can do all this math. And in reality, a lot of errors come up when you're doing a math this complicated. Could happen in the square root, could happen in the subtracting or adding, could happen in any number of places. So let's eliminate the possibility for error in our math and just use the online calculator. Plus, it saves time. And honestly, I don't care that you can plug numbers into the quadratic formula. So now what I've done is I've looked up an online quadratic calculator. I literally just type that into Google, and I click on the first one. So now you can see it gives you the standard form of a quadratic, and it tells you where a, b, and c are. So the reason I wrote my equation like I did was because I wrote the t squared terms first, which aligns with the x squared. A is the coefficient of that term. For us, it was negative 4.9. B is the next power down, which is just t, or x in my standard equation. What's the coefficient of that middle term? Well, that coefficient was 50. And then my last coefficient at the very end, by itself, was 100. So all I have to do is click calculate, and I see two answers. Which one of these answers am I going to take? Well, I can think about the fact that This is the exact same problem as the last one, except I'm letting it fall more than it did before. So it should probably take more time than it did before, and the time I took before was 10.2 seconds. So I should notice that this 11.9 is more than 10.2. That's probably my answer. I can also think about the fact that time should be positive. There's no such thing as negative time, at least not for us in this class, so any negative answer I get for time should be incorrect. So let's use 11.9 for our time. Well, now we're going to take and say, let's change this to white. Our time is 11.9 seconds. So I put that in my table. And again, I'm looking for displacement. So I use my equation that works for my x direction. Displacement is velocity times time. So the new displacement, when I let it fall 100 meters, is 86.6 multiplied times 11.9. And when you do that, you get roughly 1,030 meters. So not only did it fall longer, or not only was it in the air longer, it also traveled further. And that makes sense. If I'm spending more time in the air, that's just more time it is moving to the right also. So everything I just did here, all those steps are the exact same steps we take in our lab, except you're going to have to measure what is this y displacement. You're going to have to get what is this x and y velocity. I get that using my initial velocity and my angle, which are both in that picture in the lab where I show you what the computer tells us from the projectile launcher itself. So if you have any more questions, please message me. I hope this video was helpful, and I hope this video also helps in preparation for Test 4 as well.